So my name is Bartosz Sypytkowski. I came here from Warsaw, and for the context of this talk, I'm working on CRDTs for several years by now. And I will be also talking about the project that I'm working on together with Kevin Jans, who is author of YJS library. I'm responsible for Rust part of it. And this is a library that basically introduces config-free replicated data type for building collaborative applications. And we will talk about what problems do they solve and basically what can we use them for, what were the challenges, how could we optimize all of that, and maybe how it will be useful for you as well. So let's start with the problem statement. So the use case that we will be talking about will be a collaborative text editor, because I think that this is something that we are all more or less familiar with. We can think about Google Docs and stuff like that. However, this is not an isolated problem. We can extrapolate it into other areas. So first, we have a shared document that is being edited by several people. Every person has a local replica of that document state, right? So let's assume that two people want to insert different kind of characters in the same position. How do we reconcile that? Naively, we could try not to, so we just propagate the updates to everyone and just see what happens, right? Unfortunately, this will probably never work in practice. We will end up in corrupted state because updates are committed by people at different paces, and they are applied immediately locally on each of the replicas. So we are applying those updates in different order. This causes our application state to differ depending on the replica that we are talking about. So simplest solution is to introduce the server, right, and propagate those updates throughout the server. So before we actually commit those changes locally, we send them on the server. Server is queuing them, updating the state into some global order of updates, and then sending the updates, the replicated state, down to each of the peers that is contributing to this document. Those peers can apply this document updates locally, and they all are in the same order. Basically, we could think that this is more or less, for example, how multiplayer games are working, right? We have some local server that is our source of truth in the sense of what is the state of the system right now at the moment. But this introduces some challenges. First, we have a problem of latency. This doesn't happen often in multiplayer games because usually you have some regional servers that are co-located with our own local computers. So those latencies are usually low. However, if we are thinking more globally about systems that, well, for example, peers collaborating from, I don't know, New York to Tokyo, those latencies that are caused by communication rise from several milliseconds to several hundred milliseconds. And if you are writing something down, then you're going to notice that, right? There are different problems. For example, our editor is online only in this case, because since we have the server that is the source of truth for us, it means that we cannot really establish a correct order without this server. So this is the problem if we want to get truly collaborative experience. For example, we want to edit some document while riding on a train or on the board of the aircraft or something like that. We want to assume that there is acceptable period of disconnectivity, that after which, when we are connected to the network, we want to synchronize state, everything will came out just fine, right? A problem that is actually specific for text editing is that even in this case that we just shown with the central server, there could be a problem of characters interleaving. So two people who would be writing the entire words, not single characters, in the same position could end up in the document state that doesn't really have any sense, right? So instead of having one person's word after another's, we would have those characters that constitute into those words being mixed out. And this is correct result from the state point of view, server point of view, but it doesn't have actual sense from the experience point of view of individual writers. And of course, servers are always complicated because somebody have to own them, somebody is responsible for them, we need to scale them, there are many failure points possible in there. Ideally, you would like to omit them at all. And this is possible actually, especially in this sense. There are similar fields sharing the same problem. So collaborative text editors is one, we already talked about this. Another is cross-continental data applications. So usually when we are talking about distributed systems and data sharing, we are talking about things like, for example, Kafka and Cassandra or other kinds of distributed databases living on the servers on several machines, but all of those machines exist on the same data center when the latencies are low. If we want to move this into the interplanetary, let's say, for example, we want to move our application to synchronize data from Moon to Earth, or even between different continents, then those latency spikes and disconnectivity periods are becoming more and more visible, and they are hindering the speed of our system, basically. Another one is, of course, vehicle apps, because vehicles are not always connected to the network. So this is a good example, like applications living on the aircrafts, ships, or I don't know, trucks somewhere in the woods. And of course, remote areas. So sensor networks also living in the woods, or for example, systems working for miners in mine shafts, or similar kinds of problems. So when talking about distributed systems, we usually talk about conflict avoidance, either having a leader who is establishing one global order of updates that we are propagating, or having a quorum of usually majority of the nodes trying to establish that order. This, however, assumes that those nodes are capable of communicating with each other, and that usually there is one writer at the time for the given context of partition for a given document, or whatever is the scope of our work in particular moment. And as I've already said, this doesn't work in this particular scenarios. We want to be able to resolve conflict, because this allows us to build applications that are always able to accept writes from individual clients, basically. And this is possible if we will give enough context. And what does it mean? It all goes down into keeping the intent of our updates. So what did we really mean by promoting that updates? For example, if you are familiar with Rust, multi-threading, atomic operations, then you know that, for example, incrementing atomic counter is different kind of operation that reading that counter value, adding another integer to it, and then writing it down, right? Those are not the same operations in the context of concurrent execution. And the same is here, basically. So how do we keep intent for our particular scenario of inserting characters in the document? First off, we should probably forget about indexes, because when we are writing the words in the document, we want to write one character after another, and this is not the same in the concurrent context as writing character at the specific index. This doesn't preserve the intent, because indexes are changing over time. So something that character C, for example, appearing under the index 1, after some time might be containing another letter, another update from different persons concurrently. So the understanding of what this index hides changes over time. So we want to have something that allows us to pinpoint the identity of particular updates in one place and be able to always relate to it. And the correct name for this, as appears in the papers and stuff like that, is called Lamport clock. So we basically have a pair of values. One is the unique identifier of the particular peer of the particular machine or application instance. And we could just use, for example, GUIDs or even randomized numbers are good for that. And second is some kind of sequence number. And since those are incremented on particular machine, they are pretty easy to go because we can increment this number sequentially on single given machine without any issues because it's all executing on the single machine. Those two values allows us to uniquely identify update for globally for our entire system without having to communicate with anybody else, and this is what we are aiming for. So instead of taking insertion in terms of let's insert character B in index 1, for example, we are changing it into something like what you can see here. So we are creating a block. This can be a block of text, for example. It doesn't have to be a single character, but I will go back to this later. We add some kind of identity to it. Here it's B2. And we can say we want to insert it in between position A1 and B1. We can map our indexes because we usually, when we are working with the text document, we are working with strings and actual indexes. But if we have, for example, things like cursor, we can pin those cursor position to map into the specific logical identifiers. And here we are saying we want to insert character B that has identity B2 between some characters that is identified as A1 and B1. Okay, so how does the conflict resolution looks in that case? So given the example from the beginning, we have already existing document with two blocks A and D, and we want to two peers A and B wanted to insert something at the same position, and they've created those updates before they've got update of another peer. So this operation happens concurrently. We can recognize the unique identifiers, and we can see that their left and right neighbors that we wanted to insert our characters between are the same. So let's assume that A2 happened first. We can easily insert it because there was no extra block inside. However, when we want to insert B, there is a question where we want to insert it, right? Is it before A2 or is it after A2? We need to be able to decide about this deterministically, the same way on every machine, and even if the B2 would happen first. So how can we do it? The simplest way is to apply some kind of ordering of those identifiers that we created. Here we can assume that A is lesser than B, so we will always insert A2 before B2. So we just insert B2 after A2. And this means that even if we would apply those updates in reverse order, so if B2 would be inserted first, the total order of our updates would be still the same, because A2 would be inserted before B2 within the boundaries that we specified here, so between A1 and B1. Sorry for using so many letters and numbers. I hope that I haven't bamboozled you. So let's talk about optimization, because this was the original problem with config-free applicated data types at the very beginning. People were not eager to use it because CRDTs for a long time were not very optimized, and those implementations that were optimized were not very well known. And here we had a simple problem because we were using every update was basically a single character with 3 identifiers attached, and those identifiers we can assume that they have at least 8 bytes in size. This is 24 bytes extra of metadata for every single character, and this is crazy. It's not viable in practice. So if we could merge those blocks, it would be nice, right? Because then we could strip the metadata that is required for a merged block to ever happen in memory or on disk. And there are some cases where this is possible. For example, as one person is inserting one character after another, we can assume that those characters are being inserted sequentially. We can detect this process simply because we see that one character has sequence number for the same client happening after his left neighbor in this case, and that it's pointing, this left pointer is pointing to A1, which means that the intention was to insert those two characters sequentially and that they were committed sequentially. So if we can do so, we can potentially merge them together, because we could later on we will be able to split them in the same way. But here the block right now, it doesn't describe a single character, it describes could describe the entire text, and all we pay for is basically those 3 extra identifiers up front for every chunk of text that we want to insert instead of single character. And funny thing that YJS and Wires so far are the only production-grade libraries that use this approach, honestly. And this is also why I wanted to brag about this, honestly. So now, since this block is not responsible for holding only a single particular ID, but the entire range of IDs of characters that exist inside of it, if we want to create the next character, we are basically using formula of last ID plus the length of the block as the next sequence number. So this is why here the next block has ID A3, because A1 and A2 exist in the previous block. And it also points at the last character of the previous block. You can also assume here that our merge operation is recursive in this sense. We could later on merge this block with letter C back to our document state. And this would be fine, but there is a problem about inserting things within the block. So since the character's ID cannot change, we cannot just put any kind of character within another block, because then those IDs inside of it wouldn't present a continuous number of sequence IDs. So here, when this happens, simplest case is fixing the typo. So we have a hello world here. We want to fix the typo because the one L character is missing. We want to insert the next character. The thing is that this insertion has ID A5. We want to stick to the rules. How do we insert A5 within a block that covers the space from A1 to A4? Well, we need to split that block. However, thankfully, merging and splitting are both a reversive operation. So if two blocks were sequentially inserted, we can merge them, and if they are merged, we can assume that they were sequentially inserted, so we can reverse this whole process basically. And with this in mind, we can recreate the original block O, for example, and take the right and left pointer to point on the correct positions. And then we can insert our new typo. However, as you can see, the problem here is that this block cannot be merged any longer. This is the trade-off here. So if we are doing some pathological scenarios about block insertions, update insertions, when we are basically not typing the entire words, but I think that the most pathological case is that we are not appending to the end of the text, for example, but prepending it with a new character every time. This is the most pathological case for this particular kind of operations. But this still helps us in real-life scenarios. For example, the size. I think that Martin Klefman actually created a text editing trace of his PhD as a real-life example of a system that was built basically from 200 to 300,000 of updates. And with this approach, we basically managed to squeeze that into the update that took something like 160 kilobytes or something like that, which is pretty small for such a big document with such a great number of updates. Now, This also means, since we are able to process entire block of text as single operations, it means that the size of this block doesn't matter. For example, if we want to do something as trivial as copy-paste operation, when we want to copy-paste like 2000 characters, this also is completed as a single operation, and it doesn't take any extra time that we usually take for it. And again, you can think that this is something that we expect to happen, but the thing is that most of the CRDTs in this space don't work that way. If we would like to insert 2000 characters and copy paste them, they usually are split into 2000 separate insert operations, which is again crazy. However, with this approach, we are possible to optimize that. Thing that I haven't mentioned yet about is about tombstones. So what happens when one person is deleting a piece of document while another one is trying to insert something in between the positions that were deleted by somebody else? We cannot just do hard delete on that. We need to tombstone those blocks basically. However, there are also ways to optimize that. This is something I haven't talked about. Another thing is about different data types like maps and counters. For example, with this approach, we can also emulate maps basically. If you can think of map entries, key value pairs, and we assume that value is not a cell with a single value, but actually a list to which every insertion, every update of this particular entry is basically adding a new element at the end of the list and tombstoning everything that happened between. Then we can use the same approach to build maps. And if we can build lists and maps, then we can build more complex data types, like, for example, entire JSON documents. We didn't talk about undo and redo operation because this is something that we want to usually have in text editors, and YJS also have this. Wires doesn't have it yet, but it will be. And I think that for people who are interested in server-side stuff, the transactions are great because, for example, there is a database called AntidoteDB that allows us to create interactive transaction. Interactive in the sense like SQL transactions, when we can begin transaction, do some stuff interactively in the console, and then commit it, right? So AntidoteDB was capable of creating transactions that basically never fail. We never need to roll back them, because if we are doing transaction over CRDTs that are always capable of resolving conflicts, then we never have the issue that one transaction happened while another was still executing. Therefore, there is no need to roll back existing transactions. We can always merge them. And in case of AntidoteDB, the number of those transactions that system is capable of accepting is basically linearly scalable to the number of machines that we are adding to our distributed data system. And I think this is great, actually. And if you are interested in more, some of the CRDT projects, since we are talking about Rust, Wires and AutoMerge have Rust implementations, and they are open source. And those are both existing in the, I would say, client side of things. So those those libraries are more oriented toward building a client applications. D2Live is closed source, but is also implemented in Rust, and it's also based on the CRDT principles. They have also something that is called super peers, which is basically server-side implementation of the similar algorithm, just to help things scale. And they have like awesome network stack. I mean, their intention was to create applications that are capable to communicate over many different kind of connections, like Bluetooth, Wi-Fi Direct, and stuff like that. And they can even check which connection performs better and automatically switch onto the better connection when several alternatives are possible. ReactDB is one of the most famous ones on the server side of things. And for example, British NHS is heavy user of ReactDB. There are many betting systems that are using ReactDB. Amazon DynamoDB is, I would say, kind of primitive in the sense of things that are now available in CRDTs, but also DynamoDB was one of the first ones, and it's proven to scale highly. And AntidoteDB, I've already mentioned about this. It's implemented in Erlang. I always propose to try different things. Like if you haven't read Erlang, you should definitely try. There are also great ideas to take off from there. And if you want to learn more about CRDTs themselves, I've created over several years, I think over 15 different blog posts. Usually they have like 3,000 to 6,000 words, so they are pretty big. And if you want to have some tutorial, this is it. I've described everything that you would want to have to get started with. Like there are snippets, walkthroughs, you can go with your own algorithm implementation, because when I've started digging into the subject, there were no things outside PhD papers on that. So I've decided, let's bring this closer to non-academic people using some simpler words and actual code. There is created aggregated list of CRDTs and articles related to them. And for those of you who are interested about comparing different kinds of CRDTs with also different approaches like OTs, operational transformation, there is a person called Seth Gentle, who was author of one of the most popular OT library called ShareDB. And he recently, over the last few years, also moved onto CRD bandwagon, and he's talking about some awesome optimizations that you can do there. So, thank you very much.
Any questions?
Oh, sorry for that.
No, nothing. No.
Maybe any questions about collaborative text editors, if you are interested in that, about how we can use it in the sensor networks, in navigation, because they are also used there. I don't know how many of you are actually working on the scaling server side things. Yeah, so no.
I'm sorry.
Server side kind of things, because scalability can be achieved on many ways. Usually people are talking about servers, but one of the things here is that we don't need servers anymore, right? We can, basically every client is performing part of the task in scaling the state of the system, because also, I haven't mentioned this, but YJS has like a WebRTC connector. So you can propagate the updates using the WebRTC protocol. I'm hoping that eventually I will also create a Bluetooth connector, so you can have applications working locally and talking with each other through Bluetooth, for example. And I think that with this approach, like having all of the data locally on your machine, not having to rely on the server all the time, this is something that will be great, I think, because we are owners of our own data as well. We can scale better because server is not so needed anymore in order to scale with the number of clients, as clients can participate in this shared information sharing by themselves.